All right, everybody. How's everyone doing tonight? Good. Glad you all can make it out. Thanks for braving the weather. I think we're going to get out of here before any of the rain gets here. Fingers crossed anyway. But lovely to have you all out here. And we're also going to be live streaming this evening to YouTube. So I think a lot of people that were going to be here are watching from home. But just a couple of announcements before we get started. Make sure that you follow us on Eventbrite, which is the vendor that you got your tickets from, because we might have some other events popping up in the next few months. For example, there is, right now there's an early morning comet that's rapidly brightening and is eventually going to be in the evening skies. So who knows, we might do a special event to view that. There is a star called T Corona Borealis that has been threatening to go nova, as it has done in the past, and we might actually get to see that and have a special event for that. So go to Eventbrite, click on the follow button. It's on our website. If you just go to purchase tickets, it's that first button that pops up on their website. Okay. So without further ado, let me go ahead and introduce our speaker for this evening. So Dr. Aaron Stemo is an astrophysicist working at Vanderbilt University as a, let me get this straight, National Science Foundation Mathematical and Physical Sciences Ascending Postdoctoral Research Fellow, or as we just say, he's an NSF MPS APRF. Okay? Easy, right? His research focuses on using large collections of data from multi-wavelength surveys to better understand how our universe works, and currently he's studying how supermassive black holes coevolve alongside their host galaxies during galaxy mergers, and is developing techniques to incorporate gravitational wave observations into those studies. So it's a cakewalk, right? So without further ado, I'm going to turn it over to Dr. Stemo, and he's going to talk to us tonight about one of my favorite recent topics, which is the James Webb Space Telescope. So let's give Dr. Stemo a warm welcome.
Thank you, Billy. I appreciate it. Can everybody hear me?
Yes. Yes.
Perfect. All right. Are we all here to talk about the James Webb Space Telescope tonight? Mm-hmm. Because that is what we're going to be talking about tonight. So I just want to give everybody a warning. So when Billy brought up the idea of giving a talk, he usually solicits people in the university, like, is anybody interested in giving a talk? And I was like, yeah, I'd love to do that. And I gave a talk a couple years ago that was about what I actually do, which is galaxies. And today I'll be talking about a telescope and instruments, which is not exactly what I do. But we're mainly going to be looking at, the second half of this is really going to be looking at a lot of pretty pictures and talking about the science that they tell us, which I think everybody will enjoy. In the first half, we will talk a little bit about the telescope and what it is, so we at least all have a common ground about what we're talking about. So, without further ado, let's talk about JWST. So, very first slide, black. What I did was I was like, we're talking about all the news that JWST is coming out with all the time. Essentially, we're inundated with it. And I was like, I'm literally going to look at the last 24 hours of headlines and see what I can find. So we have this one: scientists stunned after James Webb Space Telescope spots super Earth with atmosphere covered in diamonds. And then we have another one, which is it finds a puffball exoplanet, which is lopsided. Or there's black hole feedback quenching star formation. That's more technical. Don't worry if you don't know what that is. But it means there's a supermassive black hole that's kind of spitting stuff out and making it so their galaxy can't do stuff anymore. And this is literally just within the last day or two. I think this is the oldest one with a date of the 23rd. And the idea for this talk is like, what does that mean necessarily? They sound exciting, but what are they actually trying to tell us? So this is maybe for the people who are like, okay, that's a great picture. It looks cool. I don't know what it is exactly. So if that's you, this is a good talk for you. Or if you're just the person in the friends group who is like, yeah, this is really great, I'm sure. This is also for you. And then if you really, really need a primer at the ground level, this is JWST. In case you've never seen it, this is what we're going to be talking about. It does? Well, they copied it. We're older. And this is also, we'll be talking about this a little bit later. We'll be showing off a little diagram when we talk about what the telescope, the different parts of the telescope, essentially. So, why does everybody love JWST? And now this is really a question for you, but I answered for you because I was making the slides and I did my best, which is, well, it kind of looks like a Death Star laser, personally. That's what I thought. And I was like, okay, that's interesting. it really, like, everybody loves the shape of the mirror, so you can get jewelry out of it. But really, it's that it's just really beautiful pictures, right? So I understand that. And if you really, really like science, it's really about, like, okay, that's really cool science. But really, even I'm like, they're just really pretty pictures, right? So that's why I like it a lot of the time. But as Dr. Aaron Stemo, why do scientists love this, right? Well, it is the biggest telescope in space, which just sounds like a brag, but it's actually really important for the science we do. So scientists love that it's really, really big. You can actually see it compared here, right? So this is the primary mirror of the hub of JWST, which is 6.6 meters, which is pretty good size. And this is Hubble, which is 2.4 meters. And this is another telescope called Spitzer, which was a different infrared space telescope. If you don't know what that means, don't worry, which is even smaller. You can see diagrams of Hubble, or we have a nice good sized model of Hubble right back there hanging up. And James Webb, like I said, we'll be talking about later. But you can see it's the biggest, it's the best, all right? So it's the biggest telescope in space, that's important. It takes really sharp infrared pictures. That sounds kind of trivial, but it's really not, right? Infrared stuff for like space is actually kind of hard to do. And doing it really, really well is even harder. So this is really new technology that we've been using, right? So this is a telescope in space called WISE that looks at infrared stuff. You can see it's very fuzzy, not very sharp at all. And then we have that telescope that we called Spitzer, which was a great observatory like in the 90s. It's a little bit sharper, but then you have JWST, which just has really, really good resolution. And you can see here compared to Spitzer as well, when you're actually looking at like a much better image, you can still see so much more detail when you're talking about JWST. And that's important for figuring out the why of the science we want to learn. And then, with that, with how big it is and all the other good things about it, it's really good at seeing really faint things. And that's really important because in space, a lot of things are really faint, right? Because the farther away you get, the dimmer things are, as well as maybe the smaller they are, depending on how far you go out. And that's really important if you can see them. So if you can see good, really faint things, it means you can see really far away things, which is great. Which means in space that you can see really old things, which is a little bit of a connection that we're not going to spend too much time on. Yeah, I could say trust me, but what it is there's a speed of light. It's the limit of how fast things can go, which means when something sends light to us, it takes time to get to us, right? So if something is 8 billion light years away, that means that we're seeing light from it 8 billion years ago. So we're looking at something that's really, really old, all right? So that's really interesting as well. So that's why scientists really love this stuff. All right, so let's go into a quick primer, right? This will just be, these are literally just bullet points. If you don't want to pay attention to this, don't worry. Or if you do pay attention, it's kind of like a synopsis of a few more slides that we're going to go over anyway. But either way, it is an infrared space telescope with a 6.5 meter mirror. It is launched on Christmas in 2021. I don't know who was watching that. I was. That was really fun. That was a great time. It hangs out at L2, which is a spot in space. If you know what that is, that's cool. If you don't, it's like the second Lagrangian point. It is located behind the Earth and the Moon with respect to the Sun. So if you form a line, it's hanging out back there. It is similar in resolution to Hubble. I have a little asterisk because it's similar in that how good Hubble is in the visible spectrum, it is that good in the infrared spectrum. All right, so when people are like, oh, JWST is way better of a picture, not really. Usually, they're kind of very similar if you're looking at each is like the primary wavelength they look at. It has to be really cold, right? It looks in the infrared. But if you ever use an infrared camera, if you were lucky enough, or if you know any kind of science about like humans and physics, we glow in the infrared. Anything that's warm emits infrared light. So if you are warm, you will be putting off light. So if James Webb is warm, it will put off its own light and it won't be able to really measure anything because it'll only be seeing itself. So it has to stay cold. So that's another thing we know about it. Because it has to stay cold, that means it has a limited lifetime. So unlike Hubble, which is kind of like, we're going to use you until you break, like, a 1990s Bronco, the JWST actually has it'll run out of gas essentially at some point, where it does a lot of technology and a lot of planning went into put it somewhere and have the design to try to keep it cool to begin with, but it still needs active cooling to keep it cold enough to do its measurements. So it does have a limited lifetime to be able to do that. It is the most sensitive IR telescope. This is a real science plot. Don't worry about it too much. I just want you to pay attention to like, this is something called limiting flux density. Think about how faint is something that I can see. That's all this means. And this is wavelength, which is just like, where are we? Visible light is over here, infrared's over here, right? So the lower you are, the more faint you can see, right? And you can see that James Webb is by far the most sensitive. It can see the dimmest things, right, in the wavelength regime it's in. It's even better than Hubble in the near infrared. Yeah. It has 4 science instruments. That's where I'm going to end this primer, which is when we look at it, when we use it for science, we are using 4 different unique kind of science instruments. All right. They are called near spec, which is a near infrared spectrometer. We are using near cam, which I'm sure you guys could guess, which is near infrared camera. Yep. MIRI, which is mid infrared IFU, or interferometer. And FGS NIRIS is like a field guide camera, almost, so they use it for pointing. And then the NIRIS is another near-infrared spectrometer they use for looking at exoplanets. Yet again, don't worry about following too much of this. It doesn't really matter that much. Just want to make sure if you wanted bullet points, you got bullet points. All right, so now we're going to go a little bit, just a few slides, and we're kind of going to do a little story about JWST, which is going to be like, why did we build it? How did we build it? Where did it go? What is it? Really few. And after that, I promise, all we're going to do for the rest of the time is look at pretty pictures and talk. That is all we're going to do after that. But either way, why? Why did we do JWST? Well, in 1989, by the way, which is before Hubble launched already, they were talking about what should we make afterwards, because scientists and the government love to plan decades out. So already in 1989, we're like, what are we going to do next, right? So the way you do that in science is you like, what is the goal? What are the big things we have to hit in the future? So the main goal they want to do is we want to capture the light from the oldest stars and galaxies in the universe. That's like the number one goal. That's like the single sentence goal of JWST, right? So yet again, remember this little plot or this little figure that we had, right? This is like, if we're looking back in time, I'm sorry if this is small, but I will explain this. So if we're looking back towards the Big Bang, you know, and this is modern time. So imagine the left side is modern time, and go back, we're going back in time. We're going farther away in space. So we're going closer and closer to the beginning of the universe. We're seeing older and older things, okay? So you can see that, you know, James Webb sees better than Hubble, which are these ones right here. This is James Webb. You can see the line is longer. It sees better. That's really all you need to get from that. But on the bottom, we see these things that are units. In astronomy, we have something called redshift. It's kind of like, well, what's happening to light? Light gets stretched out as the universe expands. If it goes really far, it gets stretched out, okay? We call that redshift. You don't need to know too much about it. But what we do know is that at some point after the Big Bang, right, we created the first stars, right? That's just, it had to happen because we have stars, right? At some point, we made the first stars, and we think it was about, you know, it was almost like a million years, or sorry, it was almost like 200 million years or so after the Big Bang, right? And that was James Webb's goal. It's like, I need to see things that far away. And after that, it also is able to see the first galaxies. If it can see the first stars, it can see the first galaxies. Galaxies are made of stars, so stars had to come first, right? So that's the goal, is we have to see really, really far away. In order to do that, you had to be better than Hubble, right? So this light is extremely dim, right? It's really, really far away. It gets spread out through a lot of space, which means all that light. The star only has so much light to give. It's like a light bulb, it spreads out. If you go really, really far away, all that light is getting divvied up between bigger and bigger and bigger areas that it has to try to light up, right? So these things are really, really dim by the time they get to us. And the thing about that, where I was talking about redshift, this is your, you know, 10-second explanation. The universe expands, right? There's an expanding universe that we live in. When it expands, it stretches light, right? That light that was blue kind of becomes red, okay? Think of it like a siren with a police car, right? When it's a siren with a police car, when it comes towards you, it seems a little bit higher pitched, right? When it goes away, it seems lower pitched, right? Does that make sense?
Yeah.
Good. So essentially, when the universe expands, it's kind of like the thing is going away from you, almost, a little bit of an analogy, and it stretches out the light, just like that siren is kind of stretched out when you have when you're listening to a police car. All right, so when the universe expands, it stretches out light. And when you stretch out light, what that means is you're inherently actually making a different color, okay? So your light that was blue, or the light that you can see with your eyes, and now the universe expands too much because it's really far away, all of a sudden that light is no longer visible, it's no longer blue, now it's infrared. So something that's extremely far away gets really stretched out. And since most things in the universe are kind of, peak in like the visible light, what we can see with our eyes. They're usually around there because that's what stars peak in. Funny thing, our eyes like to be able to see what stars see, So most things peak around there, but when we're really, really far away, all of a sudden that light that used to be really peaking in the visible light now peaks in the infrared. So if you want to see things that are like the first things in the universe that are really far away, you need something that looks in the infrared. You need something that can see really, really dim things. And you kind of need to be able to see really small things too. All right, so with that, they came up with this plan, and they proposed it, first called the Next Generation Space Telescope, because yet again, as the government, we're not really that original. They're like, what do we call it? No, Next Generation Space Telescope. So it was proposed in 1996. So that's how old the proposal was. But by 2002, we'd renamed it to the James Webb Space Telescope. And that's kind of where it really started its process of like having more footing as it progressed forward. Okay, so how? How JWST? How did we, what is it? How are we going to build it? How is it going to do that mission? All right, so this is kind of what the JWST looks like. We also have a little diagram, which I'm going to take out. So it is it looks pretty cool, right? It's got this huge mirror on top, right? And it's got all these fins or such underneath. These are sun shields. Remember how we said it had to cool it? So what it does is it actually kind of points this backside towards the sun, and then it uses these layers to keep itself cool because all of the important stuff is on this side, right? So on this side of the telescope, we have the primary mirror. This is called a secondary mirror. What happens is the light comes in, it bounces off this mirror to get focused on this one, and then bounces back off of that, yet again being slightly focused, onto all the stuff down here in this, this little area down here, which is leads to all the instruments, which are back here, okay? So that's kind of what you see on this. And then on the sun-facing side, which I'm not going to flip this up, but on that back side, there's antennas to talk to Earth, right? Because the back side faces towards the sun, which happens to also face towards the Earth because of where it's at. It has solar power arrays, it has steering and control, and star trackers, which means it has to know where it's going, right? So all that stuff is on the back side. So that is kind of what it looks like. Obviously, we can talk about it more as we go through, or if you have questions. But it's really a pretty open design, so it's kind of easy to get a hold of. All right. Now, remember how I talked about those 4 instruments? So this is the most important science part. It's like, okay, how are we actually going to accomplish the science? It means what are we going to put on it that can do that job, right? So we had those 4 instruments. This is going to be hard to see because I did not realize it'd be this small. So I will instead talk through this, and don't worry if you can't read it. But we're going to start with that NIRIS instrument, right? It is the near-infrared, imager, and wow, even I can't see this. Imager and slitless spectrometer. Okay, so it is mainly used to look at exoplanets, all right? That's what you really need to know. It's used to look at exoplanets. What they mean by imager and splitless spectrometer is that it's a camera, and at the same time, it takes that image and it splits it up like a prism into different wavelengths of light. That's called a spectrometer. So it does both, right? And it's mainly used to kind of look at exoplanets. It is in the near-ish infrared, all right? It is how big of a footprint it has. That's about how big of a stamp it can see on the sky. And it, like I said, has a camera and interferometer. All right. So the next instrument that we have is NIRCam, which is the near-infrared camera, right? It has 2 footprints, about the same size as NIRIS, but obviously since it's twice as much, twice as big. It sees in the same kind of area of the wavelength spectrum. It has a camera. It has a interferometer, just like the other one. But it also has something called a coronagraph, which means it can actually point at something and then block out like a small pixel, like a star. And be like, I actually want to see what's around that object. Like I want to see a planet or a really, really close by object. That's called a coronagraph. So it has one of those, which is really, really useful, yet again, for looking at exoplanets or other objects that are just really close to other objects, essentially. Near-spec, near-infrared spectrometer, is actually one of the cooler instruments, I think, because it's really, really useful for science. It doesn't make as pretty pictures, though, so, it is what it is. But it's really, really good for science. You can see that it has a pretty good footprint. It's a spectrometer pretty much exclusively, and it can do something called integrated field spectrometry, which means it actually does very much like a slitless spectrometer, where I said, it takes an image, but it splits it up. But it does it a little bit better than that. That can kind of get confused by the way that it works. This one is very much a dedicated spectrometer, so it's actually just really, really good at taking individual chunks of a picture and finding out exactly what the spectrum is for each chunk, all right? It's also in the near infrared. Then we have MIRI, which is the only instrument that's in the mid-infrared, which is just slightly more infrared, right? Near infrared is near to the visible, so mid-infrared is slightly farther away. MIRI is yet again a slitless spectrometer, just like NIRIS was. And it has a very similar footprint as well. So you can think of it very similar kind of to NIRIS, but in the mid-infrared. It has also a chronograph as well, however. And the thing about MIRI that's really interesting is that obviously it's unique on this telescope being in the mid-infrared while everything else isn't. And that slitless spectrometer is also really, really cool. So as we go through the images in the rest of the talk, you will actually notice that a lot of these things are pictures with near cam or with MIRI or both. Those are usually the primary things that we use to make really pretty pictures. If you're looking at exoplanets, maybe they're using NIRIS. But when you're looking at like galaxies or stars or nebula, you're usually looking at near cam or MIRI. Okay? All right. So when? The thing about JWST, which you may or may not know, it was delayed a lot, right? So it was originally planned for a 2007 launch, right? Remember, we said it launched in 2021, so that didn't happen. So it was delayed 12 times over the length of its development, which is kind of crazy. And it increased from a cost of $1 billion to $10 billion at the end of the day. So it kind of, I just took this straight from Wikipedia, but I just love it because it is just so indicative of like really the tortured path that we had to get to launch this telescope. You just see that price growing and it continually getting delayed. And astronomers in that like 2011 to 2017 range is where astronomers started to get really annoyed. Because we're like, yeah, it's in 2 years. You can't like say it's another 2 years after that. Like we're so close, why you keep on delaying it? But luckily it didn't get delayed further than 2021, which is good. So that's great. But I'm going to show us some pictures through the course of its development, just because it's kind of fun to watch these things, how they developed. So first really good picture that I found that I was like, this will be interesting to look at, is 2010, when we actually have this first like mirror segment that's actually completed, like this idea of like, here, these are what they're going to look like. We actually made one. This is it. So we got a nice picture of that from 2010, right? Then we have 2011, where we actually made quite a few, right? We got off the ground, we said, that's a good design, we'll make quite a few of them. And then we made quite a few, and then we started testing them. So there's a picture of multiple segments together in a testing chamber, right? And then no, I didn't skip one. 2014, we actually see all these sun shields together and assembled, which is great. So we finally get that in 2014. 2018, or 2016, I should say, we actually finished the mirrors. So in 2016 is when all the mirrors were finished. This is them putting the very last mirror into place in that array, right? 2018, we actually have both of the pieces together at one time. Down here is the sun shield apparatus, and up here is this mirror, or the mirror array where it unfolds, the whole apparatus for that. So this is the first time you actually have all the pieces in one place, right? And in 2020, we actually have it assembled, which is really cool, right? So that was kind of the really exciting time. And then after that, it was like, okay, now you just have to test it for a year and a half to make sure it actually works and you can launch it properly, which is good because it costs $10 billion. So we have it all built now. In this timeline, we have built JWST finally. But where is it going? Well, remember we said it goes to L2. I'm going to talk about that a little bit more so people understand. Right, so L2, if this is the Earth and this is the Sun, it's about a million and a half, kilometers away behind that Sun-Earth line, okay? So you can see that up here. You can see there's multiple Lagrange points. So when we talk about L2, we mean the one behind the Earth, okay? These are kind of just points on the orbit or in like the sphere of influence of the Earth and its orbit where we have something called like force balance. You can put something there and it kind of just wants to stay there. It kind of just works. Over here, it's like, okay, you're counter to the Earth. You're just going to rotate with it really well. But if you're back here, what happens is that you're actually balancing the force of the sun and the Earth, where things that are further on in orbit usually want to go slower. But because you have both those things right next to each other, you actually kind of keep up with the Earth. That's how that one works. And these ones, you're kind of balancing this force from the Earth pulling you this way, the sun pulling you this way, to kind of stay in this spot. And L1, which might be the simplest to understand, is the sun is pulling you this way, the Earth is pulling you this way, you kind of just stay put. Okay? So it's an idea of you're finding a spot where you balance in forces and you kind of usually just hang out. Okay? So we send it to L2. Why L2? Well, because it's further away from the sun, it's further away from the Earth. It needs to be able to, remember, it doesn't want to get hot. It doesn't want to get hit by a lot of light. It doesn't want to be hot. So this is kind of the best spot where it's furthest from the sun, which is the hottest thing in our solar system, as well as it's pretty good distance from the Earth. So it's out of Earth orbit. It's a little bit farther back. So that's why we chose to go there. All right. So remember, JWST launched perfectly. All of you were watching very excitedly on Christmas morning and not doing anything else. But it had a great launch. It actually was so good that they doubled the lifetime. There was originally an idea of like it would have a lifetime of 10 years. But the launch was so perfect that it saved so much fuel. It didn't have to, NASA likes to overbuild things, which is smart, but it saved so much fuel that it had planned of like, if we don't launch right, we'll have to correct our course, so we do these other things. It saved so much fuel that it actually probably doubled its lifetime, which is really, really good when you invest so much money, and it was great that we had a perfect launch. So beautiful, beautiful time. All right. It took almost a month to travel to L2, which is not that long, but it's a pretty cool process where not only did they have to kind of they had to get there. It wasn't just a straight shot. They had to kind of precisely maneuver to L2, as well as during the entire time they had to slowly unfold their telescope because we had to launch it all folded up because it was too big, right? That is a very, very big thing. Hubble was like it was actually built to spec to fit perfectly in the space shuttle's cargo bay, right? That was like kind of like we had to build it to a specification. While JWST was much bigger than that. So we had to how are we going to launch this thing, right? We kind of had that slump where we weren't really building a lot of things to get into space for a while, which happened to coincide right when JWST was supposed to be launching. So we built it so it could fold up. The mirror is just huge. We couldn't really launch that easily. So it had to be launched folded up like this, and it slowly unpacked itself as it traveled, where it kind of just unfolded its packing pallets at first, really, which is kind of like the base for the sun shield. And it slowly started unfurling the sun shield, and then it slowly started, bringing out its mirror segments as it got closer and closer. You can see it kind of unfolding here, until finally it got to its destination. It was able to settle into its orbit at L2, and it was fully open and ready to go, which was great. So once we got there, we started being able to do things like calibration, right? So what is the very first thing that a telescope does when it gets ready to start doing its job? Well, first it takes a selfie. So that's what JWST did. It was like, hey, what do I look like? Because I had to do a lot of work to get here. I had to unfold myself. Now I have to be able to actually see things. And the thing about telescopes is they're extremely precise, right? You have to be able to be aligned within we're talking like nanometers, micrometers precision. Otherwise, you're not going to really get a good image. Now imagine that you just essentially unfolded a 6-meter thing like an origami crane. It's not going to be perfect until you kind of do a lot of tweaking to get there. So it took a selfie to be like, how good am I? And the answer was, not good. Not good at all. But they did get there, and you got this really nice even image where we're actually reflecting a good flat field, which is what we want for this calibration. And then we do science, right? Yeah. So this is a beautiful picture of the Carina Nebula, if I'm not mistaken. And so this was one of the very first images that was released by JWST. They did a huge dump in July of 2022 where they started just releasing all their first images as they did this. So that's the Carina Nebula. Guess what? There's another image of the Carina Nebula. Both the same. Now you can actually see the difference. This is near cam, so which means this is MIRI, right? This is actually, I think this is MIRI with near cam, but this is just near cam by itself. And you can see that they actually look at slightly different things. Remember how I said MIRI was mid-infrared while near cam was near? And you can see that here where the mid-infrared picks up a lot of this, it gets more of this dusty features, while near cam sees it, but actually looks through part of it, right? It kind of sees a different set of this gas and dust than MIRI does. Right, we have something called the Southern Ring Nebula. This is super cool. I will talk about this again later, so I'm not going to go into it. But just absolutely beautiful, stunning photos here again. This is NIRCam, this is MIRI. And this is something called Stephan's Quintet. This is not a doctored image, this is real. There are 5 galaxies, just hanging out all right next to each other. A lot of them are interacting. And it took this beautiful, beautiful photo of this where you can actually see all these galaxies kind of messing with each other, running into each other in some aspect, as much as galaxies do. And then we got this huge thing called the deep field, right? So we had the Hubble deep field, and this was Webb saying, I can make a deep field too. I can just stare at a chunk of sky, because that's all you're doing. And it got this beautiful, beautiful image where it looked at a really good cluster, which is why you have so many things here. But also you can see all these lines and wisps all around, right? So we got to see this beautiful, beautiful structure and gravitational lensing of this area of the sky. Like literally is one of the first images that they came out with. So it was just really, really great. Honestly, really, really good first 6 months. Kind of about as well as it could have gone for the mission. All right, so I will break here because that was the technical side, at least to my mind, right? That's the part I usually don't do. So that was all the technical stuff. I'm gonna take a question break, answer some of your questions as you have for that. And then what we're gonna do for pretty much the entire rest of the talk is we're gonna look at pictures and I'm gonna talk about the science, and that's it. We're gonna look at really pretty pictures and talk about what they mean, what they tell us, okay? Yeah.
Are the sun shields big enough that they actually cause enough like solar sail forces that they have to compensate for?
I mean, the thing is, at L2, it's actually a slightly not perfect spot. So I'd say actually the dominant thing that they have to correct for is the fact that they kind of wiggle about L2. So like any solar sail effects are just at a very lower magnitude that you don't have to worry about as much.
Are there any other like systems, not including like the main 4?
Oh, the instruments.
Yeah.
Those are, well, that NIRIS is also kind of a combination field guide instrument. There's star trackers, which you might call a system. But like if you're talking about like things that we use for like really intense science, it's mostly those 4. There's a lot of other things that go into a telescope, right? We have to know where we are. That's what the star trackers are. They tell us where we are. We have to be able to do like trajectory correction. That's something called telemetry. We don't do that as astronomers. We're just like, yeah, okay, the Department of Defense, I think, usually kind of gives us telemetry kind of things. We're like, we don't do that. There's lots of things that go into a telescope. But for science, it's mostly those 4.
You mentioned limited lifetime. What is the limited lifetime? And you also mentioned we doubled it with the launch, so that's great. Yeah. But how far back do we expect to be able to see?
Okay, I love it. That's a twofer. The limited lifetime, it was originally planned for a 10-year lifetime, right? When we create these missions, we're like, if we're gonna pay this much money, we require it has to be at least this. So like, okay, we'll make it be able to at least last 10 years. But we had such a good launch that we pretty much ended up on the good side of all the error bars, right? We are like, we have to have buffer in case things go bad. But we ended up on all the good side of it that we essentially doubled it. And I think, I'm not perfectly sure, but I think the estimate that I saw was about 20 years, ideally, of a lifetime. And then how far back can we see? Really far. Like 500 million years, 400 million years after the Big Bang or so. So that's 13.2 billion years, by a billion light years away.
The brightest star on the run right there, I have that on my wall, and I've always wanted to know which one that is.
Good question. I don't either. This is the difference between an astronomer and an astrophysicist. I'm like, yeah, I don't know. But I can tell you that that's probably an O star, which is one of the hottest stars, and how they form. I don't know. Sorry.
Where on Earth was it made? Like what city? Oh, where was this made? Like when you were showing the pictures of them constructing it, where was that done?
A lot of that was done at JPL, but honestly, it was done at the Jet Propulsion Laboratory, which is in California, in Pasadena, right next to Caltech. A lot of it is done there. However, it was built in a lot of different places, and I couldn't tell you where. It was a combination of Europe as well as Canada as well.
Given that the sun shield always has to be facing the sun, is there limitations to how where the JWST can be pointed at or oriented?
Yeah, for different times of the year, right? Luckily, we orbit the sun, so we'll eventually be able to see everything. But yes, at certain times of the year, you can only see some things, right? Because you can't point too close to the sun. So you kind of have, if you had a sphere, imagine you have a pretty big wedge that you can't see at any given time. But as you orbit the sun, that changes, and you'll be able to see everything at some point. It's not that different than like, I want to go see Orion. It's like, well, you better wait until the fall because you can't see it during the summer, for example, you know? I will say, I'll give it like 1 or 2 more questions because we will go on, and we'll have time for more questions. This was kind of just a break to make sure we didn't forget anything before we got to the end.
I was curious, are the photos taken at certain intervals, or are you able to take a photo at any point remotely?
Oh, yeah, that's like a lot of money tied up in that. So what happens is we apply every October to use JWST, and it's like 1 out of every, I think it's 10 people, maybe 8 people that propose, which by the way, this isn't easy. It's like a 15-page proposal. It takes a lot of time to write, a lot of science to defend. 1 out of every 8 people that propose maybe will get approved. And then something called a time allocation committee will tell you when you're allowed to take pictures, and in fact, they'll take the pictures for you. Like they'll give you things. You don't have to worry. Don't touch the machine, kind of thing.
This might be a basic question, but when you say the time is doubled, what do you mean? Does it mean you use fuel up there, or like what? Sorry.
Yep.
Okay, it uses fuel.
Yeah.
Oh, okay. Thank you.
Yeah. So something I didn't really go into is that L2 isn't. I was going to say it's not a dip, it's a saddle. That means nothing if you don't already have it. It's like imagine that you're trying to balance a ball on the top of the hill. You can, and it is like a spot that's like kind of flat, but if it moves a little bit, it'll continue to roll down the hill unless you correct. So in that way, you kind of always have to use a little bit of fuel to do it. Does that make sense? Is it a follow-up? Yeah, sure.
So when you say fuel on board, I always assumed it was more solar powered, right? So is it some sort of rocket fuel or something that's on board, or how does that work? Do you know?
Well, you have to be able to correct a little bit, which means you have to have, well, in space, you're like, how do I move? It's inertia. So you usually have to be able to spit something out or change your inertia somehow. So you have some amount of things that you, as a physical, usually like gas or compress something, that you actually like, oh, I'm falling, I'm going to spit some gas that way, and I'll go this way then, right? Okay. I will move on because we have lots of pretty pictures to talk about. All right, so we're going to journey outward is how we're going to do this. So I'm going to start looking at things in the solar system, then we'll look at exoplanets, and then we'll look at things like in our galaxy that are a little bit farther away, and then we'll look at things outside of our galaxy. And we'll see how far we get. All right. So this is a picture of Jupiter that JWST took in October of 2023. Doesn't it look beautiful? All right. So this is going to be the recipe for pretty much the rest of the talk. So I'm going to show you a picture. I might explain it if it needs some explanation, and I'm going to tell you what's interesting about it, all right? So JWST looked at this, and it was able to actually look at, because it has such good resolution that we really didn't have before with Hubble, because it looks in the infrared, right? So it looks at a different band, and that's what you actually need to look at these images for I should say, the clouds on Jupiter, that it was actually able to have enough resolution that it was actually able to identify how fast the gas was moving on Jupiter. So it actually knows that there's a jet stream right near the equator of Jupiter that is continually moving at 320 miles an hour. So that's faster than pretty much any hurricane, on Earth, pretty much. And that's just like, that's the jet stream. Like, it's like the Gulf Stream almost, but way, way faster here on Earth. And this was something that, was only be able to identify because of the unique nature of JWST. All right, Enceladus. So Enceladus is one of Saturn's moons. All right, so this is just a picture from a different satellite called Cassini. So it took a nice picture of us, but we're actually looking at something else. This is that NIRAS instrument, right? So it looks slightly different, but this is really interesting because this is water vapor. There's a huge plume of water vapor coming off Enceladus. So this is actually when I say it's not to scale, this little square is like the size of this square. So this water vapor plume that's coming off of Enceladus is like 20 times the size of the planet, right? And is about, I'm going to say 80 gallons a second of water. Doesn't sound like a lot for a planet, but remember it's a moon, It's on a planet, so it's kind of small, and it's giving off 80 gallons per second of water into that plume, and that is fueling Saturn's rings, actually. So it's kind of like just dumping water into Saturn's rings and making it look really pretty, right? So not half of that, 30% of it or so is purely from Enceladus giving water to those rings. This is Uranus. It has beautiful pictures. These are actually two different pictures, so it took one in April and December of 2023. So here we're actually looking at the ring system that looks really, really good with JWST, right? Because we're looking at a different wavelength band. We have good resolution. But also, you can actually see the polar cap on Uranus with these ones. So this actually white region is the polar cap on Uranus. Notice that it's actually sideways. Uranus is one of those weird ones where it kind of is sideways. So you'd expect the rings on a system to be kind of around its belly with it as it rotates, but actually Uranus is tilted on its side. So it's actually a little bit unique in there. So you can see that they're actually able to see the polar cap, but they also, in this image, they were actually able to see that there is a unique kind of unknown previously reflection or high albedo of the polar cap on the North Pole that's kind of on the other side, which was unknown at the time. The right image was actually really cool. You can actually see 9 of the 27 moons of Saturn all around these. Every little dot is a different moon. That was great. So let's get Neptune's rings now. So there's a picture of Neptune. These rings have not been seen since 1989 by Voyager 2 as it went by. And then JWST was like, I can see them, which is great. So we know that Neptune is usually blue, right, from methane, but it's barely visible right here. It's really, really dim, right? Does anybody know what this is? Or could guess? Yeah.
Sun.
Oh, that is actually a very good guess. Why did you guess the sun?
Because it kind of has like the thing, and if you look at a star in the night sky, it kind of has that same thing. So
Yep.
that's what I thought.
They're called diffraction spikes. It's because they're really bright, right? So this thing is really, really bright compared to Uranus. That is actually a moon of Uranus. That is Triton. So it's crazy that the moon is just so much brighter than Neptune, and that's actually a fact that methane absorbs infrared. It's a greenhouse gas, in case you guys didn't remember. So it absorbs infrared, so it makes it actually really, really dim because it's just not letting infrared out. So JWST is just like, oh, you're really dim. It's still warm, so it sees it a little bit, but it's just way dimmer than, for example, a moon. But the ring system on this is absolutely beautiful as well. All right, we're going to talk about some exoplanets, which are my least favorite. But anyway, so they looked at WASP-B. This was WASP-96b. This was actually came out in the first like initial dump of stuff. They're like, I'm gonna give something to every kind of astronomer right now. So like, here's the exoplanet thing they gave to people. Was they looked at this system, right? It is a really big planet that orbits another sun. You can see that they find it by something called the transit method of detection, which is essentially you look at a star and you see if it becomes dimmer. And if it becomes dimmer in a really specific way, like this, it means that something went in front of it. And if it happens a few times, you know that it has a planet going around it, essentially making the light dip. And then they were able to use, yet again, NIRIS, to essentially stare at that thing, and they're actually able to tell you what's kind of in the atmosphere of that planet. And the way they do that is actually in these little shaded, you see how this edge case is? There's a time when the planet's blocked out, but the atmosphere isn't, and vice versa. And that way you can actually kind of get a little bit knowledge about the atmosphere of the planet. And then what they were able to find is that there's a ton of water in that atmosphere. It's a very, very steamy Jupiter is essentially what it looks like. This is great. This is a protostar. So this is essentially one of the stages before you turn into a real star. You're not a real boy yet. You are, and the reason is it's not actually doing fusion. That's how we define the start of a star. But this star is only like 100,000 years old. It's really, really young, this protostar. These clouds are actually only visible in the infrared. This is essentially gas and dust that is being kind of spewed out by this protostar that's really, really hot. It's rotating really fast. A lot of stuff is trying to fall onto it. Not everything can fall onto it because it's kind of spinning. So that's some stuff just kind of gets slung out as like almost like a messy eater kind of thing. And when it does that, all this gas and dust hits the gas and dust, like the other gas and dust around it, and it kind of heats it up. So essentially you can imagine I'm almost throwing spaghetti and hitting things, and they're getting color from the spaghetti almost, right? So that's what we're seeing here, is really, really beautiful color from this protostar that's right in the middle. You can actually see this little dark band if you have good eyes or in the front row, luckily. That is actually the kind of like the disk like what will turn into planets eventually of that star, right in the middle. And all this is the stuff coming out from either side. Oh, by the way, if there's anything like I don't understand, ask a question. If it's kind of like that's interesting, let me ask a question, that can wait. But if it's like, what is that red? Feel free to like just raise your hand real quick. This is another exoplanet system, AU microscopy. So essentially, we're looking in two different bands here. So this is we use color for whatever, for the different bands. Just they're called false colors. So this is essentially something that is higher energy and lower energy, or more red, more blue. All right, and we're essentially looking at the disk of a very young red dwarf, which is essentially a very small star. And we can see that it's extremely dusty here. And what we know is that because of how old it is, that it essentially has two planets, they think. But the thing is that is a really, really dusty disk for a star system, that in fact we must be looking at the stage where the planets have formed, but there's still a lot of like tiny planetesimals that are slamming into each other and essentially making this really dusty disk, which is really interesting because it's a phase of like star formation and planet formation that we really just don't have a lot of knowledge about. So it's really interesting to be able to see something like this and study it so we can know more about how our solar system formed, for example, or how they form in general. Oh, yeah. All right. Extrasolar systems. Yeah. The Orion Nebula, which is one of my favorites. I love also you can see through telescopes. If you have a good telescope, I think you can see the Orion Nebula really well here when it's, and actually at the fall, you'll be able to see it soon, obviously not during the rain. But it's one of my favorite things to look at in a telescope. But what's really cool is that James Webb looked at this region, looked in MIRI, looked in NIRCam. This is NIRCam yet again. You see this beautiful, beautiful nebula. It looks amazing. But what they found was actually they found a very unique carbon compound. They found something called methyl cation. And what it is, it's really interesting because it is thought to aid the formation of more complex carbon molecules, which is kind of like a stepping stone to creating life, we think. So we're like, oh, we didn't think this thing could be formed, or like, how could we form it out in space? And the thing is, they found it. And what's really interesting is the Orion Nebula has a lot of young, hot stars that are putting off a lot of ultraviolet radiation. And some theories are like, if you have too much ultraviolet radiation, you destroy your molecules and you can't make things. But what they're saying is actually you need some in order to make this molecule. Like you need a little bit of energy to put that thing together. So that is actually a really, really interesting discovery and gives us, more knowledge to how we can look for organic compounds or maybe life in the future. I put this in just for fun. This is the loneliest exoplanet we've seen to date. This is the coldest exoplanet we've ever seen, which is interesting because almost all the exoplanets we see are really, really big and really, really hot and really, really close to their stars because those are easier to see for like how we find them. So really, this is just a testament to how good JWST is at finding these things. It's about the same. Essentially, this thing is about the same as Jupiter. It's very similar to Jupiter, which is saying a lot because we never find things that are close to like our gas giants. They're almost always hotter or closer. So we're actually able to find a system that is very similar, has a gas giant very similar to those in our own solar system. And that means we can study that and actually learn some things from an extrasolar planet to the ones in our solar system much more closely. All right, we're finally getting to things that I really like. Stars and nebulae. Cool. All right, remember how I said we'd talk about this again? So on the left is NIRCam, on the right is MIRI. This is a beautiful nebula. It is actually from a white dwarf. It's like a dead star. When a star dies, it really puffs up and it shoots and it kind of like puffs off all of the shells of gas all around it. Something our sun will probably do as well. And what happens is as it's getting older, it's like puffing up, it's shutting all these layers, and it turns into a white dwarf. That's kind of what's left over. And actually, this was, we've only ever been able to see it like with Hubble and stuff before. We only ever saw one star at the center. But the thing is, we know that's not what would actually create these rings or what created this nebula, because that's just a star. But we know that a white dwarf, it has to be a white dwarf left over that made it. But with MIRI, with JWST, we're actually able to see that white dwarf partner here. So this little dot on the right is actually the white dwarf, while that thing on the left is that other star. So we can actually see its partner here, which is really cool. This is the Tarantula Nebula. This is a really, really cool, honestly, really cool picture. This is that $10 billion wallpaper machine really coming into play here. So this is a nebula that's in the Large Magellanic Cloud, which is essentially that little dwarf galaxy that's next to us, one of them. If you're in the southern hemisphere, you can see it. It is extremely active in forming stars. That's what all these little blue dots are. These are all like a whole bunch of young stars all forming at the same time, all this gas and dust around it is like, will turn into stars, most likely, or at least a lot of it will. And the resolution that we're able to get from JWST, it allows us to see a lot of the details of this and really see how these things are forming, outside of our galaxy and like the Large Magellanic Cloud, which is slightly out away from us. So it's slightly different than us. We get to understand how that works as well. What's really cool here is you can actually see when these things form stars, they get really hot and they push against all the gas and dust around them, and they kind of carve out huge cavities, right? That's what creates these. Otherwise, you'd kind of just look like this. But when you make stars, they get really hot and they hit gas, and the gas is like, okay, I guess I'll kind of break apart, because I'm too hot. I can't stay together. And it creates these huge cavities. But in some spots, you can almost see these tendrils form. Like this one is one I like a lot. So you see almost like, this is going to be impossible to see, maybe far away. Trust me, there is a tendril of gas here that is forming almost like a strand of hair. But the thing is, that means it's resisting that attempt to be kind of pushed away, which means there's actually another star at the tip of that pillar that is forming, and it's actually able to hold that gas and dust by it. It's essentially able to be like, I have a lot of gas and dust too, you're not going to push me away. And it's able to form almost these pillars that like push into this cavity almost, they look like. This is the pillars of creation. I have no science to actually, this is like the only one where I don't have any good science to say that's novel. It just looks amazing. This is NIRCam on the left, this is MIRI on the right. And I just want to highlight some of the differences between the two, where you can see through a lot of this gas and dust here. And you can kind of see through it here if you wanted to, but really what we're seeing is a different like a type of gas, essentially. We're looking at a different kind of gas because we're looking at a different section of the wavelength of light. And you can just see the very different thing. Where you can see these stars at the tips. So remember when I said about those pillars that are pushing back against that thing, up against the effect of the other stars trying to disassociate or push their gas away? That's what's happening with these pillars of creation. That's what these are. There's stars at the tip of these, and there's like a huge nebula over here, essentially, right? So there's a whole bunch of stars forming. It's pushing against this, and these stars here are holding that gas together, essentially. And here you can't really see them too much, but you know they're there. But then if you look over here, you can actually see that star that exists at the tip of these pillars, possibly. They're a little bit dim. This one's brighter, this one's dimmer. You can see this one right here really well. And essentially you're able to see through and see some of these stars that are existing in that proto-star state, getting ready to kind of turn into real stars. So this is actually the closest star-forming nebula to us. It is only 400 light years away. Now, we've never really been able to see this that well, the gas and dust dynamics of this, right? Kind of all this energetic behavior that's happening, because we just weren't looking in the right wavelength. Essentially, we had Spitzer, or we had Hubble. Hubble looks in the visible light, not the right region. And we had Spitzer or WISE, which looks in infrared, but doesn't have the resolution to tell us what we need to know, right? So now JWST does. And in this region, the reason it's interesting why we study it is because there's about 50 sun-like stars being born in this nebula currently, right? And what's really interesting is all this stuff up here, all this red, this is all gas and dust that's being flung out by these stars. Remember how I talked about the one earlier that looked like that protostar that almost looked like a hourglass? Right? That's like, there's a whole bunch of those doing this. So this is one jet, right? There's a star here that's flowing off this way. There's one right here that's going this way. There's one over here that's going off that way and that way. This one is going this way. And you can see all these different stars essentially interacting with each other, growing and turning into essentially things that will turn into our sun. And it's really close by, and we're actually able to study it now, which is why it's really, really interesting and new. It gives us insight into how our sun was formed. This is the Crab Nebula. This is also formed from this was formed from a supernova explosion. So not like a white dwarf, which is kind of just puffing up and like shedding layers. This one actually exploded. So essentially there is a remnant. There's a pulsar, which is a neutron star that's really magnetic at the center. And it's at the center of this. It had exploded. And the really interesting thing that JWST let us see, right, before Hubble could see a lot of this structure, but see all this like white, wispy, cloud-like gas almost? That is actually gas that is being energized by essentially the magnetic field of that pulsar. It has extremely strong magnetic field, and what it does is it puts off something called synchrotron radiation as it spins, and it energizes all this gas and this white gas all around it, which is something we really weren't able to see. And it gives us a lot of insight into essentially how that star blew up, what it was made of, how the process went, and what was the result of it. We really learned a lot about how it works. And you can actually see it's kind of hard to see, but it kind of exists right here. And if you got a really good zoomed in picture of it, you'd actually be able to see all this white gas almost look like it's swirling around this spot, which is really cool. Yeah. Since I don't want to go too much over time, I'm going to like skip this one a little bit. I just really want to say it's another nebula. But what's really interesting about this is that they all have these, remember how we talked about these protostars with like little jets? You can see up here that a lot of them are kind of going in the same direction, right? This one kind of a little bit, this one a little bit, this one definitely. All these are kind of aligned. That's actually novel. Like, we have theory that they should do that, but this is really good evidence that it actually does that, which we didn't have before. It's kind of this idea of like there's this general way that things spin, in a cloud, and as they collapse, they maintain that. And that makes sense, like from a pen and paper point of view, but this is actual evidence that kind of supports that, right? Because they'll end up all kind of going the same direction. This is 50,000 light years out. There's another nebula forming stars. The thing is, the gas and dust here is really pristine. It doesn't have a lot of metal in it, right? A lot of the stuff by us does, because stars explode, they put out metal into the universe. So essentially, the more pristine your gas is, the less metal you have in it. So if you're outside of a lot of galaxies, if you're kind of in this like region in like the halo and outside of our galaxy, you have really pristine gas. So by looking at this, we can actually learn more about how these pristine stars were formed, which actually does tell us about how earlier stars were formed as well. Okay, guys, we're finally getting to the stuff I really, really love. I love stuff that's outside of our galaxy, okay? So this is that cluster. Remember, it was that first release of like the deep field. And I want to point out some really interesting things, right? We have a star, of course, but we have a really, really massive kind of like central galaxy in this middle. And that has so much gravity that what it does is it actually warps light around it. So all these weird things that look like they're kind of forming almost like a circle around it, all these weird stretched out things, that's because the light is being warped from behind it and being warped around it, almost like a lens. It's called gravitational lensing. So we're actually able to see a lot of galaxies that are actually behind this cluster that maybe we wouldn't normally be able to see because they're being bent around it and magnified. So that's actually really, really cool to see here. You can also see this. This is not a normal shape for a galaxy. So you see that. Here's that Stevens quintet. This is near and dear to my heart because I study galaxy mergers. And so I study galaxy evolution and what happens when they kind of run into each other and what happens. And this is just a beautiful photo where you can actually see two cores right next to each other. This one is already interacted. You can see this thing right here. This is called a tidal tail. Essentially what happens is like your gas goes by and the other one friend goes by and they kind of just zoom by each other and they kind of take little wisps of each other as they go by. And that's what we call a tidal tail. And you can see that really nicely here. But it's also just kind of insane to see 5 interacting galaxies. Like, normal is 2. 3 isn't crazy. 4 is kind of rare. 5 is, I think this might be one of the only ones. I really don't know of any other one. It's kind of crazy. But it's an amazing photo that shows you a lot of that structure of how these things are being impacted, right? So we see all this extended features. So here's one of the big pieces of news, like, oh, the theories of cosmology doesn't work. Galaxies are too big. Too big, too early. If you're like really deep into the science of news that comes out of JWST, this is one of those things that came out that told us that. It's like we're looking really, really far back, and we're looking at these really, really old galaxies. Z of 10.5 is like less than 1 billion years after the Big Bang. It's really, really, really old, and we're like, that is a huge galaxy for that old. Like, they shouldn't be that big by then, right? Because you'd have to take time to make stars to build up a galaxy. They can't just be huge immediately. They have to come from somewhere. And we're like, this doesn't make sense at all. We cannot explain it, right? So we're like, I don't know. There's been a lot of disagreement since then. So there's been a little bit of something that came in, and I'll talk about that in like a slide or two. But it kind of really upset the entire scientific community for like a year, where we're like, we don't believe you. Like, that sounds nice, and I see your evidence, but it's got to be something wrong. And we were right, though. Okay, so here's another really, really deep image, something called a cosmic filament. So essentially, the idea of like really, really large scale structure in the universe is that things kind of like to be next to each other because of gravity, and they actually form something called a cosmic web. Like, these galaxies will want to be by each other, but everything was kind of spread out really evenly at first, so the kind of things all condense into clumps, and in between those clumps there's little like strings connecting them. We call that a cosmic web. And one of those strings is called a filament. So essentially what these people found is that they found one of the oldest cosmic filaments that's ever been seen. This is this is a string of 10 galaxies that all kind of form a line all along the same distance from us. So they actually are like a string in like 3D space that are all about the same age. And it's from 800 million years after the Big Bang, which is like the earliest we've ever seen this kind of structure kind of pop out. So this was really, really cool. Also, one of these is a quasar, which is a supermassive black hole that's eating in a lot of gas. And as it eats that gas gets really hot and gets really bright, which means that it can actually outshine the galaxy. So this is also really interesting because, yet again, these things are really, really rare that early too, because like, how big can you make a black hole? Like your galaxies shouldn't even be big. How's your black hole at the center going to be that big as well? So it's a really, really interesting find. This was really interesting. This is a little bit more technical, so I'm not going to go into detail. But this is a really interesting piece of news, is that we know in space there's a point where like gas and dust in the universe was just like kind of hard to see through, right? It was kind of like molecules, not atoms, right? Because they were like, it's kind of cold enough that I can kind of just chill with my friends. But then at some point, we formed enough stars and quasars that they heated up the gas, and they no longer could be like that. And that's what we call reionization. Essentially, at some point, we hit all that gas with too much light from the stars, and now you can see through it again, instead of it kind of being hard to see through. And what they did was they were actually able to find one of the earlier quasars and prove that it had enough energy to be able to do that reionization when we thought it did. This is just a picture of the oldest star we've ever seen. This star, we only can see it because of gravitational lensing, yet again, because it kind of magnifies it and lets us see it. It's only 400 million years old. It's down here somewhere. It is so hard to see that I can't even put it out on the photo that should make it easier to see. We'd have to have a nice, really big zoom in. But honestly, it's the spectrometry that allows us to know that it's a star and how old it is. This is just cute. This is called the penguin and the egg, if you can see it. So yet again, this is a merging galaxy, so near and dear to my heart. This is one of them. This is the other one. You can see galaxies shouldn't look like this, right? So this almost looks like a half of a spiral galaxy, kind of like the Milky Way. But this side does not at all, because it's been passed through. They kind of pass by each other. And like I said, they kind of grab a little bit of each other as they go by. But what's really interesting about JWST is you see this kind of, yet again, like those really light stuff. That actually shows us that there is a connection between the two still. And these are actually sharing gas and stars, right? That where they kind of pull on each other a little bit, they are not separated. They actually are connected, like truly actually connected in some way. Even when they pass by each other, they still kind of leave a string of connection between them, right? So these two, just holding hands essentially. This is a whole nother galaxy. It looks really dim though, right? The reason it looks dim is actually because it's very, very bright in the visible. It has a lot of blue stars, but guess what? Blue stars are not nearly as bright, in the infrared, really. So it's actually a little bit more dim. This is a very young, not dusty galaxy. So it's not really as bright in JWST as you think. Hey, remember how I said those people were wrong? They were wrong. So this thing proves it. Essentially, they looked at all these galaxies and these yet again, really, really deep images. Yet again, like some of the first galaxies, these deep fields, just looking at a whole bunch of really, really old galaxies. Like, hey, this one and a lot of things that look like it, they're actually normal mass. They just have a lot of really, really, really hot gas. So as astronomers, we kind of make empirical laws for pretty much everything because we can't prove things. We don't have a laboratory we can put a galaxy in, right? So we have to be like, okay, what do we see? But we make those predictions based on things near us because they're easier to see, right? We haven't been able to see this far before. And the thing about stuff near us is that they don't have as much hot gas. Most of that light from a galaxy comes from its stars, but not with these old galaxies. A lot of that light actually comes from hot gas. And when we try to estimate the size of a galaxy based on the idea that most of it comes from stars, but it's not, we're going to say that there's more stuff there. We're going to say there's more stars there, but it's not more stars, it's just hot gas. So those things earlier were like, our stuff doesn't work. It does work. They're just way more hot gas than we expected. So they're not as big as we thought they would be. They don't break any cosmology. They're just they kind of just have a different properties than the ones we normally see because they're older. All right. Okay, guys. I'm only 8 minutes over, but I think I started a few minutes late, so we're kind of good. All right, so this is where I'm going to end. And I promise you what's coming up next, but then I ran out of time really putting in pretty pictures. I kept on, I was like, from that I can tell you some of the things that we are looking to do, which is some of them is that we want to look more at those water vapor plumes off of Enceladus. We want to understand that more. Some people want to look at Kuiper belt objects, things really, really far in the universe or in the solar system, these icy objects, and be like, what are they like? Like, where's that ice? Some people want to look for exomoons. So not just exoplanets, that's not good enough anymore. Now they're like, I want to look for moons around exoplanets. So that's like some proposal they're trying to do. And the thing is, JWST is good enough to do that, right? We actually want to see older and older stars. So we want to get a better understanding of the diversity of these oldest stars in the universe, as well as we really, really want to understand these old supermassive black holes. Remember, I was like, oh, there's these old quasars, and they have a lot of impact on how the universe looked back in the day. But we want to study more of them because they're honestly, it's a really complex subject. And we need to know how they act because they act different, kind of like at every chunk of time that we go back in the universe. They kind of always act a little bit different. We want to know how they got there and how they grew. So those are some of the things that we're doing, like literally within the next year. Actually, probably actively. It's like the papers will be coming out soon, actually. And then the really energetic people in the field will be submitting more proposals to use JWST in exactly 1 month, I think. I think it's October 26th. I could be wrong. But essentially then we'll put another cycle out and try to observe more things with it. Yeah, that is where I'll end, so we have time for questions. Yes. Oh, wait. Sorry.
The question is in reference to the merging galaxies and the gas exchange that ends up happening. Is it a true gas exchange that's happening, or is it like an equilibrium that's reached, or is there a half-life of these gases where one is dominating and the other?
Yeah.
Or gravitational pull?
For sure. It depends on where you are in this process. In this image, it's most likely that they are not truly like completely intermingled. What's most likely is that there's streamers from both sides that are connected in the center, and like at some section of that, they are intermingled, but otherwise it's mostly one, like a little bit from each that come together and then connect in this example.
So it would just stay in this view?
Oh, no, absolutely not.
Right, okay.
No. So these things are most likely flinging about each other. Is not going to work, but right. So these two galaxies are coming at each other, and they kind of want to come towards each other, but they're not perfectly lined up, so they shoot by each other. It's called first pericenter passage, and that's probably what these things did. So when they do this, they kind of drag a little bit of that gas towards each other, and they slowly come back around, and the gas actually kind of causes them to slow down and kind of cause them to merge more, right? You kind of create like a little bit of drag by all this stuff interacting that you slow each other down and you eventually merge.
Oh, okay, cool.
Yeah. Yeah.
It's my understanding that Andromeda is going to slam into us in a couple billion years.
That's true.
What would it look like to be in a solar system involved in a merger such as this?
There's actually a really, really good animation on like YouTube. I'm not going to try to pull it up right now, but so galaxies slamming into each other is kind of like snow falling. Like nothing's going to hit each other, really. You know, there's too empty. Space is very empty, so nothing will hit each other. But essentially, everything will kind of run into it, just like how I described, and eventually like intermingle. And how it would look while you, like from the surface of Earth, for example, is that essentially Andromeda would get bigger in the sky, it'd get brighter in the sky, until eventually what happened would be there'd be just like, essentially there'd just be a lot of stars in the sky. Like it would kind of just look like really energetic, because also when galaxies merge, they make more stars, and new stars are bright. So essentially there'd be a lot of bright stars in the sky, there'd be a lot more stars that you can see with eye by the sky, until things settle down, and eventually we'd probably turn into a different kind of galaxy, which would mean there would be a diffuse galaxy instead of like a Milky Way bar, for example. So it just look a little bit different. But I highly suggest you look at a video online. It's like 30 seconds maybe.
Yeah, and I was going to say we have the animation stills on a graphic in the hallway.
Go look at it.
So what are we working on next? If this is only going to last for 20 years, are we already creating the next telescope, and what will that look like?
Yep. The next one is probably going to be either an X-ray telescope or an ultraviolet telescope, depending on the size you want to make. Europe is launching some as well, right? So we're no longer like the only people really making the really, really big observatories anymore. So Europe is making some as well. They're making like a really big X-ray telescope, for example. The next one for the US, I believe, is supposed to be maybe an X-ray as well, or is it the ultraviolet? I don't remember. Do you? Oh, geez. I didn't even, like, that's already in my head is like, yeah, that's done. It's good. Yeah, no, the Nancy Grace Roman, which is essentially like a super Hubble, essentially. It's like Hubble, except for where Hubble can kind of see like a really tiny footprint. Nancy Grace Roman can like image the entire moon or something like that in like each snapshot. but it has the same resolution. It has the same sensitivity. It's just huge. So it'll, instead of where Hubble kind of was only able to like take little postage stamps of the sky everywhere, and it was actually really hard for them to do like that deep field that they did. Nancy Grace Roman will essentially be able to do that without any problem. It'll make just huge swaths of the sky really, really well seen. Yeah, that's like I said, my brain was like, it's like, I was like, it's done until I get pictures, is how my brain works. I'm like, I don't know, sometime later this decade, maybe? I think so. Yeah.
Do any of the telescopes study antimatter, or is that still theoretical?
None of them study it directly, but if you, there's some that study really, really high energy light, like gamma rays, and we also study like high energy particles as well, called like cosmic rays, and those are kind of would be the result of antimatter interacting with matter. So in that way, we kind of study it, but not directly.
How much cleanup goes from whatever the data is that's snapped and then sent to us? Do we, open up Photoshop and tweak the curves and the brightness and stuff like that? How much do they do before we get this image?
Yeah, there's a whole 6-month grad student class that teaches you how to do data reduction from observations. But essentially, yeah, you have to correct for things like how hot is my detector, and I have to be able to quantify that. How much noise do I have in my data? Is the sky brighter than it was yesterday for some reason? Like how much ambient electricity exists in my circuits currently? All these things are quantified. There's usually 4 different kind of calibration images you take along with every science image in order to calibrate it properly. But with everything like this, they're so expensive and there's so much work that goes into it, we create a pipeline before it ever launches. There's a pipeline that all we do is here's the data pipeline, do it for me kind of thing. And it's usually, it's quite a bit of work, but it's a little bit automated. And then if you work at the place that actually runs the telescopes, you have to worry about it more. Me, I'm just I just want this, I just want the usable science picture, please. And if you're making public image, public facing images like this, then you actually go into people who are doing things like, how do I make this actually intelligible to people, right? What I get a black and white photo of the 3 different colors. I get 3 photos that are all black and white, and I have to understand okay, this is 140 or this is 1.4 microns, this is 2.4 microns, this one is tracing oxygen, and this one tracing hydrogen. I don't get a pretty picture. I kind of get the more base level thing of why do you need a picture? You can get the science from the information, right? But when you want to see it like this, that's when we're okay, if this thing is a longer wavelength, people think that's red. A higher energy thing will be blue, because that makes more sense to our brains, and it kind of translates to the right thing that we're trying to tell you with the science. And so you balance color, or you do false coloring, it's called. You do color balancing, you do image, light balancing, right? Stars are naturally very logarithmic with how bright they are, and these images are usually not, right? So you have to correct that. It's just a different scale of how you look at the light. So there's a lot of different things that go into it.
Yes, so if we see the light that is infinitely old, and it's taken 13 billion years to reach us, how do we know that particular source, that star, is even there anymore, emitting light?
Oh yeah, for sure. We don't. Absolutely we don't. There's no way for us to know it's there anymore. But at the same time, if all we ever see is the past, it's real for us. You know what I'm saying? It's it's essentially it is the time. It is like the Goonie said, it's our time. We see it when we see it, and we get to watch it in real time, but it's just our time and not theirs. So it might not be there, but for our case, that doesn't matter that much. We can't be there. We can't get there tomorrow. It's 13 billion years away. So I don't know.
Let's do one more.
If you could point this thing anywhere, that we haven't seen yet, hasn't had pictures taken of yet, what would you point it at?
First of all, lovely to see you.
Yeah. Happy to be here.
That's a really good question. I would never point at the sun because it would break it, but also I don't like the sun. Yeah, that is an awesome question. Wow.
Or is
I can
there
tell you, I can
an
tell you a
event you'd
sample
like
of
to
20
see?
objects that I'd really like to see. What was that?
There we go. So, same thing what you just said.
Yes, I have a paper that's waiting to be published where if I had really detailed images of about 20 galaxies, it would be really great for me. So I guess that's where I'd point at. Yeah, I mean, if I was just like, what looks interesting, honestly, they've done a really solid job of like getting beautiful pictures. They've already looked at a lot of the nebulas I want to see. That's true. Hubble has a panorama of the Carina Nebula that I have printed out on my wall, and I'm waiting for JWST to do the exact same panorama, and they didn't. Instead, they're like, we got this different section of Carina, so we're not going to look at it. I'm like, it doesn't match. I want like one for one, the twin of it. So I guess that's what I would do, purely for aesthetics.
All right, well, let's thank Dr. Stemo for a fabulous presentation about Webb. We need more presentations like this where we focus on the pretty pictures. So thank you for bringing that to us. Dr. Stemo will be hanging around for a little while, so if you have any other additional questions, I'm sure he'd be happy to take some. We're not going to be able to view anything through the telescope tonight, but if you would like to go up and see our telescope, especially if it's your first time here, Dr. Bob Schweikert over there at the doorway would be more than happy to show you and answer any questions you might have. So thank you all for coming this evening, and for our folks at home, thanks for watching, and we will see you next month.